So we're moving into sort of the next phase of the program today. So you've heard about wildfires, you heard about wildfire smoke and contributions to air quality. Then really now the theme of the rest of the day is what about indoors? And the first consideration is certainly what happens to outdoor air as it gets indoors. So we're really pleased to have Bill Nazaroff from the University of California, Berkeley. Bill's one of the world's leading indoor air quality experts. Been working on this for a long, long time, and great to have you here, Bill. So,
thanks, Michael, for the introduction, and thank you to the organizing committee and the BC Lung Foundation for the opportunity to be here today. So, how does outdoor air pollution affect indoor air quality? That's a significant slice of the broader space in which I work. And the particular pollutants that we'll be taking a look at are two of the big ones, particulate matter and ozone. Globally, I still find these numbers shockingly high, and I'm not going to try to defend them except to make the qualitative point that PM and ozone-associated health impacts register very high on the causes of ill health worldwide. So this is a result summary of some data from an ongoing study, the Global Burden of Disease. Worldwide, in year 2016, all deaths from all causes of anybody numbered about 60 million. And almost, or somewhat over 10% of those are attributed to exposure to air pollution. And the big factors within the air pollution space are particulate matter, responsible for more than half of the total according to this assessment, and ozone, which also contributes significantly, but not on the same scale as PM. But of course, one of the limitations of that class of studies is that the pollution that we are assumed to be exposed to is what's measured or modeled in outdoor air. And people don't spend their time outdoors. These bar graphs show the results of a couple of survey studies, one done in the United States and one done in Canada, of time apportionment of populations. These are average, sort of the average person in Canada and the United States. And you can see there's no difference between the two countries, or at least the differences are negligible. But the more important point that I want to convey is that we spend most of our time indoors. In fact, most of that we spend in our own residence. Of course, we spend nominally a third of our time in our bedroom sleeping. But even in addition to that, another comparable scale of time spent indoors in our home doing other things while we're awake. We spend another 18% of our time in other indoor environments on average, and only 5 to 10%-ish in the two other compartments, outdoors and in vehicles. So in rough terms, we spend a factor of 10 more time indoors in our home than we spend outdoors where the air pollution is well characterized. So it raises the really important question, what are we actually exposed to when there's pollution outdoors? And this is the first very important point for me to convey to you, that indoor air is not outdoor air. It's not outdoor air, although the pollutants that are present in outdoor air can be transported, are transported with ventilation that is either deliberate or inadvertent through leaks in the building envelope. Those pollutants do come indoors, but they're transformed indoors through a variety of processes, some deliberate, most unintentional. And so even in the absence of indoor emissions of pollutants, the indoor air composition does not match the local outdoor air composition. And that's the part that this talk is going to focus on, the ways that there's a mismatch. Furthermore, and I won't be talking about this very important point, pollutants can be emitted indoors. And this is germane for the subject of today's workshop, because as we try to protect ourselves from pollution that originates outdoors, wildfire smoke, for example, that may have influence on our exposure to the pollutants that are being emitted from indoor sources. So we do need to take that into account. I just don't have time to do the full space. So my talk's going to focus then on particles and ozone in outdoor air, and how much does the building protect us from those pollutants. For particles, I mean, it's an almost unfair comparison when you say particles are much more important than ozone. Ozone is a molecule. Particles are a whole category of things. Many molecules, it's the zoo where the ozone is just one species of animal in the zoo. And one of the important features of particles is the size of the suspended condensed phase material in the air. So represented just by diameter, a characteristic diameter, we could have 5 orders of magnitude span from the smallest things that we would call particles that might only be a nanometer in diameter, up to the largest things that would be suspended for any reasonable period of time, which is about 100 micrometers. So we subdivide this huge space into smaller categories, and the one that we'll focus on in this talk is PM 2.5. That's the one that's most carefully monitored and regulated. That's the mass concentration of all the condensed phase materials, the micrograms of that material per cubic meter of air, whose aerodynamic diameter is smaller than 2.5 micrometers. So that would include ultrafine particles, although they make up a minority of the mass. And for wildfire smoke, the more important part is the accumulation mode, which is typically in the size range between 1/10 of a micrometer and 2 micrometers in diameter. And by the way, one of the really interesting and actually valuable communication elements is that highly sophisticated instruments are not necessary to have a sense of what the PM 2.5 level is in the atmosphere, because it correlates really well with haze. I have 2 pictures here taken in Singapore when I happened to be there exposed to a regional smoke event, and they're taken at the same location. The difference in the fine particle level was a factor of about 40. The difference in visual range was even greater. Now, a lot of complicated things happen to particles in indoor environments, whether those particles were emitted from an indoor source or come in from outdoor air. But for much of our interest, particularly in this context where we're trying to get an overall sense, we can talk about a much simpler representation of the story where we hide all the complexity into a single factor called the infiltration factor. So this infiltration factor, symbolized Fi sub INF, is the fraction of the particle concentration that you would have originating outdoors that is present in the indoor environment. It spans the range 0 to 1. If it's 1, the indoor concentration of particles of outdoor origin is the same as the outdoor concentration. If it's 0, the building is completely protective against particles of outdoor origin. So if we know this infiltration factor, then we can constitute a relatively simple model for the indoor particle levels to which one might be exposed, shown by the equation here. Multiply the infiltration factor against the outdoor particle concentration, and then add a contribution from indoor sources. And that construction is even among scholars working in the indoor environment. A lot of us spend time trying to understand what this infiltration factor depends upon, but a lot of us also talk about, okay, we know what the infiltration factor is. What does that mean for the exposure of people in indoor environments, for example, to pollution of outdoor origin? I've compiled in this figure data from the last 45 years, which is roughly my research time span in this space, but it's also roughly the time over which studies have been conducted that report on infiltration factors for PM 2.5 in residences in Canada and in the United States. Each one of the data points is the central tendency reported value for a population of homes in one of the studies. And many of these studies didn't report dispersion about that central tendency. They just told you what the mean value is. So that's robust, but doesn't tell everything that we might like to know. And then they're listed from top to bottom just in year of under which or in which the study was conducted. And the important points that I want to convey are shown in the yellow box here. First, the overall central tendency aggregated across all these studies is 0.5. So if you have 10 micrograms per cubic meter outdoors, the best guess at what you have in a residence in North America is 5 micrograms per cubic meter, attributable to that 10 outdoors. But even in central tendency, these dozen or so studies span a range of a factor of 3. That is, the mean or the median in each of the studies could go between 1/4 and 3/4. And then individual homes, of course, could go even more broadly than that. Now, let's take what we know and take a look at what exposure would be and where the exposure is occurring. So exposure is a term that has it belongs to the vernacular. We have some sense of what it means, but it also has a technical sort of quantitative meaning. And the way we should be thinking about exposure is that exposure accumulates over some period of time as the product of a concentration to which we encounter, or that we encounter, multiplied by the duration over which that encounter takes place. So here we take a day, and I've just broken it up not in proper time series, but in the 3 or 4 categories of where we're spending our time that day in the bottom plot and on the bars on the left. 2 hours spent outdoors, 1 hour in a vehicle, 17 hours in a residence, and 4 hours in some other indoor environment. Slightly stylized, but based on the Canadian and US survey data. And then I've assumed we have 10 micrograms per cubic meter of PM 2.5 outdoors, and we have an infiltration factor applicable to all the indoor spaces of 0.5. So the PM level then that's encountered by this hypothetical person going through their day is 10 micrograms per cubic meter when they're outdoors or when they're in a car, and it's 5 micrograms per cubic meter when they're in the indoor environment. Their aggregate exposure is the area represented in either the bar chart at the bottom or in the pie chart, which disaggregates this area into its respective sites where it occurs. And here's the takeaway message, that even though the building provides 50% attenuation to the particles of outdoor origin, most of our exposure, no surprise, occurs indoors, because we spend 10 times as much time indoors as we spend outdoors. So even that 50% level of protection is not nearly enough to make the indoor environment unimportant. And in fact, the numbers work out to about 63% of the exposure occurring in our residence, 15% in other indoor spaces. So 78% better at math than that. 78% of our aggregate exposure, about 3/4 in this hypothetical scenario, is occurring indoors. And in terms of modulating factors, whether the indoor environment is a 25% infiltration factor environment or a 75, is going to be really big in terms of its consequence for our exposure. All right, now I want to get down into the weeds a little bit about those details of the factors that go into the infiltration factor, just so that you have a better basis for understanding some of the things that are kind of glossed over in this one big number. The first important point to convey to you is that the particle size is the size distribution that we would find in outdoor air is going to be shifted when those particles come indoors. And that shift occurs because the smallest and the largest particles do not penetrate and persist as well in indoor environments as the intermediate sized so-called accumulation mode. They're called accumulation mode because they tend to be most persistent outdoors. It shouldn't shock us that they're also most persistent indoors. They don't deposit as rapidly on room surfaces. They're harder to remove by filtration. And so the infiltration factor is higher for the particles of this intermediate size, the smoke particles, than it is for the freshly nucleated ultrafine particles or from coarse particles that might come from road dust or tire wear, for example. The building operation absolutely can affect the infiltration factor. These data are from a study in Hong Kong, but they are, I think, pertinent and informative here, where 3 different factors were explored in a large survey with respect to how they impacted the infiltration factor for PM2.5. And you see from the box and whisker plots that the most significant influence has to do with window opening. That's seen in the plot on the left. So in conditions where in this kind of warm climate, people were able to keep their home windows closed, they could reduce the infiltration factor down to roughly a quarter, whereas when the windows were open a significant part of the day, the infiltration factor was 0.75 or 0.8 in central tendency. Air conditioning played a role, partly because it correlated with window opening behavior, and the use of an air cleaner also played a role. One weakness of this study is that we don't know anything from the reporting on what air cleaners were used, how efficient they were, what their capacity was, and so forth. So I think air cleaners generally are more promising than revealed in the data from this Hong Kong study. The chemical composition of particles also changes between indoors and outdoors. And I'll just point out 2 ways in which that happens. They both have to do with semi-volatile species, that is, species that can partition between being in the gas phase and being associated with condensed phase. One big category of those is organic compounds, and we tend to have much higher levels of broad suite of organic compounds originating from indoor sources that might be cooking, they might be the building materials, it might be personal care products that are used by people, leading to the volatilization of some organic materials indoors, and many studies now show much higher organic levels indoors than we find outdoors. Some of those will partition onto particulate matter. So the data shown in this slide come from a study in which we made a detailed investigation of a home over an extended campaign, a few days of which the house was vacant. And in this detailed characterization, we monitored not only the indoor and outdoor particle levels, but we also monitored the chemical composition, the organic chemical composition of the particle phase and of the gas phase. And what I want to point out is the 2 slides at the bottom, in which on the left you can see an infiltration factor here that would be roughly a quarter, 1.2 micrograms per cubic meter indoors when the people were not present, the house was closed up, compared to the 5 micrograms per cubic meter outdoors. And in the plot on the right, you can see an enhancement in organic component of the indoor particles. These are indoor particles of outdoor origin, particles that come in and acquire organic material that came from the gas phase emissions, in this case from building materials, solvents and so forth, and from the furnishings, and led to higher levels of alkanes, alcohols, and so on associated with the particles that had originated indoors, causing the particles to increase in mass somewhat. Conversely, the figures don't help support this as well as I would like, but a very important inorganic component of particulate matter outdoors are, well, the combined, or the whole class is ammonium nitrate and ammonium sulfates. And ammonium nitrate in particular is semi-volatile. So if the temperature is warmer, then ammonium nitrate particles will tend to dissociate, and the nitric acid that's formed through that dissociation will go to interior surfaces. So this tends to happen in the wintertime, and these data come from the Central Valley in California, where there's a lot of nitrate pollution from farming activities and from motor vehicles, and we also have a lot of ammonia from agricultural practices. And so we have high ammonium nitrate levels, cold outdoor conditions. The air comes into a building, and those ammonium nitrate particles can actually volatilize, causing the particles to shrink with the nitric acid going to the walls. So if we know particles are bad for us and we're trying to take refuge from smoke, can building operations actually lead to improvements? We have a little bit of evidence, and not a trivial amount, showing that yes, in fact, deliberately lowering infiltration factors is possible under high smoke conditions. And these are data that come from a Purple Air monitoring network. The authors of this study, let me explain that the three bars on the right, or the three sets of bars on the right, the three frames, show cases in California, Northern California in 2020, Northern California in 2018, and Southern California in 2020, comparing conditions when there was fire impacted PM levels in red and no fire in blue. And the violin plots just focus on the central tendency here, not the enormous dispersion. You can see infiltration factors, at least in two of those three cases, significantly lower when the fire was taking place because people were taking actions to protect themselves from the fire. And what were those actions? They were indoors with the doors and windows closed, and in many cases with air cleaners operating. So the authors of the study, I quote here, reported that we found that geometric mean infiltration ratios were reduced from 0.4 during non-fire days to 0.2 during wildfire days. We find that common adaptation measures, including reducing ventilation and active air filtration, effectively mitigate average indoor exposures. And in fact, we know a lot about how to attenuate indoor particle levels with filters, with particle filters. There's a well-established marketplace. There's a lot of junk out there as well, so it requires skeptical but not cynical buyers in order to use this marketplace wisely. But I've just highlighted here a few important elements. MERV rating system. So MERV is minimum efficiency reporting value, and a MERV 13, 14, 15 filter is much better for air quality improvement, reasonable to put into a fan filter unit, such as this do-it-yourself box, the Corsi-Rosenthal box on the right, relatively inexpensive to assemble, or one can buy off-the-shelf units from reputable companies, including those with HEPA filters that do recirculation, and these are characterized in terms of a clean air delivery rate, and what one wants to compare is the clean air delivery rate to the leakage or ventilation rate at which outdoor air is being brought in. You want your clean air delivery rate to be at least on the same scale, if not larger, than the ventilation rate. We expect, and we have some evidence to support, that there are disparities across the population in the infiltration factor. And some of these would make the problem of smoke protection by buildings more serious in low-income housing. We know that low-income housing tends to have a leaky building envelope. There's more reliance on window opening for cooling in hot conditions. There's lower prevalence of central forced air heating and cooling systems, which can have good filters installed, and lower prevalence and usage of air cleaners. And U.S. National Academy's review was published recently on particulate matter and indoor exposures and protecting oneself in indoor environments. Some key conclusions quoted here: ample evidence that exposure to indoor fine particulate matter causes adverse health effects. Disparities exist in population exposure of both indoor and outdoor origin. Technological advances have great potential for quantifying and reducing exposures. There's effective and practical mitigation in schools and homes that is possible. And we, in the United States at least, lack a central responsibility for PM policy indoors, which is hindering achieving higher levels of protection in this space. I think in the interest of time, I'm going to skip my story of indoor ozone, unless you've got excess time. Skip it. And close with just the summary of, I edited a journal called Indoor Air for about a decade, and toward the end of my time, I tried to write a, as concise as possible, set of guideposts that we could look at for summarizing what do we know really about indoor environmental quality writ large and how to improve it. And so I came up with 4 ideas expressed in 12 words, and then a few years later realized that I really needed a 5th one. And so here they are. Actually, the one that we focused on here today was protect against outdoor pollution, and also considered ventilate well. Minimizing indoor emissions, also critical. Keeping the indoor environment dry, because a lot of indoor problems associated with moisture that's uncontrolled, and then focus on the needs of our occupants. These don't explain how you achieve those goals, and there's a lot that has to be done. There's a lot that we know that isn't being done well, and then there's a lot that we don't yet know that we ought to know. So there's still a lot of room for improving our indoor environments, one big part of which is going to be to have them better protect us in the future from increased wildfire smoke. Thank you.
So thanks.
I like this standing ovation.
You like this? We can do another one for you. Thanks very much. And we'll take, I cut you off from the ozone so that we'd have time for questions. If you do have questions about ozone, feel free, or anything else. So Chris, do you have? Let's go to Connor first.
Thanks very much. Connor Reynolds with Metro Vancouver's Air Quality and Climate Action Group. And we're doing a lot of work at the moment on how to retrofit buildings in order to get better energy efficiency and lower GHG emissions, right? And part of that is tighter envelopes and switching to electric heating and cooling. And so one of the things I'm thinking about here is, as you get this shift towards tighter buildings, you're potentially protecting against outdoor air contaminants from wildfire smoke and other sources. But then you are dealing with increased issues with indoor air sources. And I know you didn't really deal with that here, but I think this is a very interesting trend. I think it's happening all over as we're dealing with extreme heat. People are closing windows, they have tighter buildings, they're turning on AC. So, one of the things we obviously want to see is more electric appliances, electric heating and cooling, which should reduce indoor air pollution sources. So my question is, are you aware of studies that are kind of looking at the potential exposure to air contaminant impacts of this shift in building policy approaches? And any other thoughts related to that?
Yes, there is some scholarship in that space, but it's what you've described as a smaller part of a big envelope of how have things changed over the past decades with different building materials being brought into practice and so forth. I want to answer not quite the question you asked, though, but the way you phrase the question makes this an important point for me to convey. I think the buzzword among people who I'm near neighbors to, the ventilation of building engineers, is build it tight, ventilate it right. And so it's not about building a tight envelope and then stopping there with internal recirculation so that you have a accumulation of indoor emitted pollutants, but it's providing ventilation appropriately to the space under controlled conditions rather than relying on occupant-used operable windows. And half an air change per hour, that is half the volume of the residence, being replaced hourly with outdoor air is kind of the nominal target. Air-to-air heat exchangers in places where the climate is extreme, like Canadian winters, would probably be appropriate, certainly to consider. So there are ways to do that in an efficient manner, and more energy efficient manner than just uncontrolled infiltration.
Thanks. Yeah, go ahead.
Norman Development Club Director. I was just wondering, Generally speaking, how do air conditioners affect the indoor quality of a home?
Yeah. Well, so most air conditioning systems in residences don't provide ventilation. They just recirculate the air, at least that's their design, through a cooling coil. And there are two strong features in addition to the influence that one may have on ventilation. So first, let's take up the influence on ventilation. If the house is too warm and you don't use air conditioning, you're going to open the windows, you're going to have a higher exchange between indoors and outdoors, and that's going to make the indoor air look more like the outdoor air. You have higher infiltration factors of all the pollutants, less impact of indoor emitted pollutants. If we're just dealing with, air conditioning on or not on, then the difference in temperature has an effect, because VOCs that are emitted, volatile organic compounds that are emitted from indoor source materials, have emission rates that scale with temperature. So cooler conditions is actually better for lowering exposure to these contaminants. There's another important feature, which is air conditioning operation tends to dehumidify the interior space. You get condensation of water on the coils, that water drains away. That reduces concentrations of organic acids that might be in the indoor air. That's been seen empirically now. But the drier conditions can also kind of fit under the let's keep it dry mantra to reduce exposure to certain kinds of pests like dust mites. So it's not a simple story. It's multifaceted.
Take one more. Yeah, go ahead.
I just got a quick question about how you mentioned keeping it dry, but in the wintertime in an apartment building, say with electric heating, it's dry and some with lung conditions, we're coughing and that, so you use a humidifier.
Right.
So the humidifier makes it feel much more comfortable. Is it doing anything to help reduce or change the particular size inside, or does it just give you a feeling of comfort?
So for the sake of those online, I'll just highlight what the key part of the question is, and it's in wintertime. Oh, apparently it went through. I don't have to redo that. So it's another one that has multiple dimensions. Our sense of comfort can definitely be disturbed when the humidity gets too low, although interestingly enough, when you fly, you're also exposed to extremely low humidity. And one of the sensations that we have of dryness in flying is actually not attributable to the dry conditions. It's been tested in the laboratory, but rather to air pollutants that are present in the aircraft cabin. Sometimes it's ozone, because we're flying into the lower part of the stratosphere. And so there is this, and it's sort of an unexplored or underexplored question whether a humidity below 20%, say, in indoor environment in the wintertime is manifestly unhealthful, or it's just uncomfortable for some reason that's not because of the humidity. My leaning is that it's probably not particularly healthful, but one does need to be careful about two things with humidification. One is condensation occurring on interior surfaces that you want to avoid at all costs. So if your windows are not particularly high quality, you may start getting condensation on the window panes, and that can lead to mold and mildew. And then the other is the manner of humidification. One style of humidification is ultrasonic, which makes little droplets that then evaporate. If you use that method and don't use very high quality distilled water, you end up adding particulate matter from mineral impurities in the water into the air. It becomes part of the particulate matter load. That's not a good thing. Steam humidification is better, but then you have to be careful about mold growth in the reservoir that's getting heated up. And so some good maintenance is required for the humidification unit.
Thanks very much. And I should say we have an ongoing battle with physicians actually recommending humidifiers and not giving these cautions, and seen many cases actually where you increase mold growth when people are using humidifiers. So thanks very much. Again, encourage you to interact with the speakers during the break that's coming up, and we'll come back in about 20 minutes. So thanks very much again.